All right, here we go. Got a little chemical vortex going here. Looking kind of cool. So what we got here is a, what do we got? A magnetic stir plate going. I've got a flask here with some universal indicator in it. And I'm going to add a little bit of, let's try adding some base to this, see what happens. Here we go. So we'll add a little bit of base, a couple drops, and you're going to see a color change, of course, to science is the best, Arjun. It sure is. So you're going to see a huge color shift there. So what I've got, again, in here is some universal indicator. Sometimes it's called rainbow indicator. It varies in pH from, hey, Thomas, I'm doing well. Varies in pH colors from pH like 11, which is a violet color, down to pH 3, and pH 3 is going to be a reddened color. And right now the solution's fairly basic, so I'm going to add some acid, try to change the pH. The acid I'm adding is hydrochloric acid. Hydrochloric acid is also known as stomach acid. I'm doing well there, Thomas. Here we go. We're going to add a few drops of hydrochloric acid. There's one drop, 2 drops. So what happens when I add the base, it's going to neutralize, the acid, it's going to neutralize any base that's in here. And it's going to lower the pH. You might also see just a little ball that I've got flying around in there. That's just a Nerf ball I like sticking in there, a ball for a Nerf gun. So as the acid is added, the pH drops. And along with that, you see a change in the color. So right now, it's looking a bit blue to me. That's going to be a pH of about, 9, maybe 8. If I can get the pH to be neutral, it'll look green, like that. And that'll tell me right here that the solution has been neutralized. So we have completely neutralized the Dunkel. Haven't done a titration in a while, huh? Good to see you on here, Dunk. Anyway, this is neutral. We're going to keep adding a little bit of acid here, and that should lower the pH, sure enough. Yellow, that's going to be a pH of 5, maybe 6. Add another drop. That pulls us to orange. That's going to be a pH of like 5 or 4. And if I can get it all the way down to red, that'll be a pH of about 3. There we go. There's a whole bunch of interesting effects we can get going on with this. Of course, you can see I got one of my son's balls to his Nerf gun in there. This kind of just flies around in the vortex. That's kind of fun. Actually, this looks kind of orange. I'm still thinking we're about a pH of 4. Let me add just a little bit more acid to get that down to a nice red color, pH of 3 or so. Hey, thanks for the love from India, Treaty Bot. I am in the United States of America. Let's jack up the speed of the stir bar here. You get some interesting effects when you do that. Sometimes you'll see, there we go. You'll get some bubbles in there. Gives a nice little color to it. Sometimes sometimes the ball, there we go. We'll get the ball out, because the ball will knock the stir bar out of orbit, so to speak. Let's get it caught back here. There we go. Get it rifling. See if we can get a nice vortex going. Sweet. And we're going to change that pH back in the other direction. See if we can get a little rainbow going. Rainbow tornado. Can I show how to dilute a concentrated acid? Well, do what you oughta. Add acid into water is what we say over here in the United States. Okay, here we're going to add some sodium hydroxide base. This is found in oven cleaner or drain cleaner. Here we go. Hey, thanks, Rahu. I appreciate knowing that you've tried some of my experiments. Let's try a drop of base here. Boy, we see a bunch of different colors there. So what happens when I add just a drop? Looks like we've relaxed at about a pH of 5, I'd say. You know, there's before the base and acid completely get mixed throughout the whole solution, there's going to be regions of different pH within the mixture until it's homogenized, and that's why you're going to see a bunch of different colors at once. That's nice to see sometimes. Let's get this really going here. All right, I'm going to add a little bit of acid here. We're going to add some stomach acid. Thank you, Caleb. Hello, Brigadish. We'll add a drop of hydrochloric acid. Add another drop. Getting a bunch of different colors at once. Very nice and pretty. There we go. Add a few more. Getting some interesting different colors at the same time. You know, I think the colors persist, the different colors persist a little longer if I turn the speed of the stir plate down. So you don't get as nice of a vortex, but you do get some interesting effects. I'm going to turn this down just a bit. There we go. Get a slower stir speed going. We're going to add a few drops here of the acid to get it nice and red. pH of about 3. And now let's try adding some base. See what happens here. Here we go. Add a few drops. And you can see right in the middle, you got like a purple vortex going on. And then as it mixes through the solution, you may see a bunch of different colors all at once. As the mixture tries to homogenize, the acid and the base react with one another, neutralize each other, we see what pH we end up with. It's looking to me like we may have ended up at a pH of about 6, just below 7. It is kind of cool. You see those two like bubbles beneath the vortex there? I see that effect sometimes too, which is kind of interesting. I don't really know what's going on there, but it's cool to see. Hey, Mamura, how you doing? Thanks for joining in. We'll add a little more base. Boy, look at that nice purple vortex we got there in the middle. And as that base spreads out into the surrounding solution, it looks like we're going to be at a pretty high pH. I've completely... hello, Batman. I'm shortening your name. I think you know why. So I'm, you know, the base completely diffuses throughout the mixture. The indicator I'm using, Casper, is universal indicator, also known as rainbow indicator. It's going to be violet colored at high pH, around pH 9 or 10. Excuse me, around pH 10. As I add acid to this, I'll add 1 drop of sulfuric acid, also known as battery acid. That's going to neutralize the base. And actually, wow, that not only neutralized it, it also added an excess of acid, and we saw a huge pH change, getting us all the way down to a pH 3, that nice red color there. We'll add a drop of base, send us back in the other direction. This is 20% sodium hydroxide solution. In the middle, you can see that purple vortex, and you can watch it spread out into the surrounding solution, and the solution's trying to figure out what pH it's going to land at, so you'll see multiple colors. Looks like we're at orange to me. You're welcome, Casper. Which tells me we're at a pH of about 4. Add another drop. Boy, that's a beautiful vortex there in the middle. I don't know if you all are seeing that. Let me see if I can get this light just a little better. Maybe able to see a little more what's going on. Oh yeah, I've added quite enough base now that the pH is rather high. We're at a pH of about 10 or 11. Nice violet color. I've added HCl, H2SO4. What bases have I added? The only base I have present is sodium hydroxide base. It's the only one I got with me. I don't have any others currently on hand. Different concentrations, though. I do have several different concentrations I'm playing around with. So let's see here. We want to send this back and then send the pH down. So I'm going to add some 1 molar hydrochloric acid. Let's add like... iOS user, what is giving this the color is an acid-base indicator that we chemists like to call universal indicator or rainbow indicator. Probably for obvious reasons at this point, you can understand why we call it rainbow indicator. And an interesting fact about rainbow indicator is it changes color depending upon the pH of the solution. And so the solution now is a pH of about like 3, I'd say, and that's giving us our red color. And as I add base to the mixture like I just did, that base is going to react with the acid and neutralize it, bring the pH up. And as everything mixes together and homogenizes, looks like we're going to end up with a orange colored solution. That tells me the pH is about 5. We're still somewhat acidic. I'll add another drop of the base, see if I can neutralize the acid that's in there. Uh-oh, I think I lost my seal. Let's try that. Oh, here's a bunch of drops of base. Let's see what happens here. Beautiful vortex. I'm hoping that we end up with a green color. That'll tell me that the pH is neutral. So what's the final expected product of all the acids that have reacted with the base? What salt do we expect? Right now we're at a pH of 6. Let me just add a few more, see if I can neutralize it, get us to pH of 7. That depends on which acids and bases I've reacted together. So if I'm reacting sodium hydroxide with hydrochloric acid, if that's what I'm mixing together, then the final product will be water and sodium chloride. That'll be our salt, regular old table salt. If I'm mixing together sulfuric acid and sodium hydroxide, which I do on occasion, my final products will be either, actually both of these, depending on how high the pH is, sodium hydrogen sulfate or sodium sulfate. Is this the same indicator as in pH strips? Yes, as in some pH strips for sure. Universal indicator is indeed used in many pH strips. And by the way, universal indicator is not a single indicator. It's a mixture of them. There's 3 different, if I'm correct, if I remember correctly, there's 3 different indicators in universal indicator that allow you to get those many color changes at many different pH values. Hello, Ken, is this too? Welcome. Yeah, we got a nice high pH here. Violet color. Sometimes people call it the grimace solution. We're going to add some some hydrochloric acid, stomach acid to this, a few drops. Try to get that pH to drop. That's 4 drops of hydrochloric acid to our solution of sodium hydroxide. As the solution mixes, it's not quite homogenized, so you're going to see a bunch of different regions with a bunch of different pH values, and it's going to give you a bunch of different colors. It's a nice little effect that you get to see sometimes. Beautiful looking. Beautiful looking. Keep adding our acid. pH will drop. Good night there, Batman. Okay. I have methyl red in powder form. How much do I need in order to make it a liquid indicator using the kind of bottle you use for the universal indicator? Okay, so here's my guess. This is generally how I make my indicators from indicator in the powder form. You're going to want to take some type of alcohol. It could be isopropyl alcohol. It could be ethyl alcohol. You're going to dissolve roughly 0.05 grams of your indicator powder into about 100 milliliters of the alcohol. And then to that, you'll add an equal volume of water. So another 100 mils of water. If that's not giving you the deepness of color that you wish, then you're going to want to, use more of the solid. But generally speaking, when I make up my indicators, I use about 0.05 grams of the powder indicator and put that in 100 mils of the alcohol and dilute it with an equal volume of water. And of course, red cabbage, Casper, and thanks for chiming in on that. Red cabbage does an awesome job. You just boil some red cabbage and pour off the solution, you get a nice universal indicator. It doesn't have the same color changes that you see here, but you see some nice ones nonetheless. Let's check out another indicator after I get this one. We're going to use phenolphthalein. So this flask I have prepared, this one here, has phenolphthalein in it. With some common pH indicators you get. Some easy ones you can get, again, are red cabbage. Believe it or not, blueberry extract makes a nice indicator, a red-blue indicator. White clover, I have found, gives you a colorless yellow indicator. So does methylated spirit work for the alcohol bit? You know, I'm not exactly sure what you mean by methylated spirit. I imagine that's fairly nonpolar. The issue with that is it's not going to be very soluble in water unless it's methyl alcohol. So the issue is usually when we're doing, you know, indicator experiments, like the one you're going to see here, I'm going to add a little base to this phenolphthalein indicator. Look at that. Look at that little pink vortex you get. The issue with methylated spirit is, I'm not 100% sure what you mean by methylated spirit, but I'm guessing it's a very nonpolar mixture. And the problem with that is it's not going to go into the water real well. So that's why we tend to use alcohol to dissolve our indicators. And you don't need much. All right, let's give 1 drop of base to this phenolphthalein indicator. We're getting a nice pink vortex. Look at that. That's gorgeous. That's so pretty. It's like a phantom vortex. It's really cool. And then we see if I've added enough base to neutralize the acid. If so, the pink color will persist. If not, it'll slowly fade away. Isn't that cool? All right, 3 drops. Let's see if that's enough to neutralize the acid. This is the fun way of doing titrations. And not quite enough. 3 more drops. Oh, I think that one's going to last. Maybe not. Maybe not. There may be too much acid. Sure enough, away it goes. I'm going to have 1 drop here. We're getting close to the equivalence point where there's just the same amount of acid and base. Look at that. Not quite. Another drop. Uh-oh. It's called methylated spirit over here in Nigeria, but it's used for disinfecting injuries. Yeah, I can't. I imagine it's probably an alcohol. Then it may work there, Christian. Give it a shot. But what I would do before is, you know, just make sure that the methylated spirit mixes very well with water. If not, you know, if you see a separation between the two, it's probably not gonna work real well. Depending on what you're trying to do. Add a little drop of acid. See if we want to go back to colorless. Sure enough, neutralize the base. Let's see if we can get that pink vortex going again. You're welcome. Anytime, Christian. Thanks for joining in today. Couple drops there. Hey, Detonator. Good to see you. Yeah, I've been spending a lot more time doing my lives on TikTok. I get a lot more views over there on my lives on TikTok. So, you know, naturally I spend a little more time over there. Yeah, I might get, 100,000 views sometimes on my lives on TikTok. So I spend a little more time over there. You can follow me on TikTok if you haven't. I'm under my name, Tommy Technetium, but I also go, my handle is PChemStud. So if you want to give me a follow on TikTok, make sure you say hi. Say, hey, I saw you doing this over on YouTube. Oh, that stinks, Detonator. TikTok is banned in India. I did not know that. That shows you what I know. Thank you for letting me know that. You guys are keeping me up to date in the world. Appreciate it. It's good to learn. You see that little faint pink color? I think I'm like at the perfect place right now. There's just a faint pink, which probably tells me that the acid and base are completely in balance. They're completely neutralized. Pretty in pink, indeed. Builder rat. Yes, indeed. Let's add a little bit of base here. See if I can get that the pink vortex. I see many of you are not on TikTok, huh? There's your pink vortex. That's going to last. Let's give a drop of battery acid, send it back in the other direction. Oh, away it goes. It's going to go. I think that's going to take it. Maybe not. Oh, I'm going to need a second drop. Maybe not. Oh, look at that faint pink. Just a faint pink. I think it's going to go. Yep. Well, no, I still see a faint pink. If you look up at the top of the vortex, I can see it on the... man, is that ever just barely there. I'm wondering if it's from this. No, it's there. Very faintly pink. We'll have one more drop. There we go. Now we've acidified the mixture. All right, we'll add a bit more sodium hydroxide. Get our pink vortex going. 3 drops. See if that lasts or not. Yep, I think it will. Nope, indeed it didn't. All right, I want to get that pink vortex to last a little longer, so I'm going to increase my stir speed. I'm going to add a bunch more acid to the outside. So that's 10 drops of acid. Can I describe where the protons are going? Sure. Unfortunately, I don't have a chemical structure of phenolphthalein with me. But phenolphthalein can be considered a leuco dye. You're seeing the leuco form here, leuco meaning colorless. And when the protons are removed from the dye, from the leuco dye, it actually opens a ring there on the phenolphthalein, and that ring opening, as the loss of the proton from the phenolphthalein molecule, causes a ring opening in the molecule, and that ring opening is what causes the color change. And then if we can add protons back on the dye, that's when you go back to the leuco structure. That's a great question. I should probably bring some pictures of the structures with me next time. Nice purple vortex. Can we make mass with energy? Yes, the indicator is phenolphthalein, MlM5. Okay, so depends what you mean by that, detonator. So there is a law of conservation of mass in the universe. So the mass of the universe is going to stay constant, as is the energy in the universe, minus quantum fluctuations. So, overall, the mass of the universe stays the same. The energy of the universe stays the same. However, you're describing a specific system, like, say, a radioactive atom. That particular system can lose energy, and when it loses energy, it also loses mass. So those two go together, of course, as you know, via E equals mc squared. So I have to be real careful, we all should, describing, say, converting mass into energy. I mean, we use that language a lot, and basically that means if, a system loses mass, it also releases energy. In other words, it loses energy, and we can use the energy released, to do stuff. But we have to recognize when the system loses mass, it also loses energy. And that mass and that energy are picked up by the surroundings of whatever system we're looking at. MlM5, exception of the law of conservation of mass is nuclear energy. Well, I'm going to push you a little on that MlM5. I want you to listen carefully what I'm saying here. This is interesting stuff. It really is. There is a common misconception that, nuclear processes violate the law of conservation of mass. But we have to be careful. The law of conservation of mass says the universe itself, the entire universe, will not lose mass. So what that means is when a nuclear process goes, like we'll say nuclear fission, so uranium splits into krypton, and what's the other one? Barium, if I remember correctly. I think that's right. So when uranium fizzes, the products have less mass, indeed, than your original uranium. So if you look at the 3 neutrons that come off, you look at the 2 atoms that come off from the original uranium, it is in fact the case that those products will have less mass than your original uranium atom. But that's not a violation of the law of conservation of mass. Now, that may sound funny to you, and good for you if it does sound funny. But here's the deal. While the system of uranium and all the matter contained in the uranium lost mass, that mass went into, the surroundings. And you say, how in the world could the mass have gone into the surroundings? Well, because as the uranium undergoes fission, it releases energy into the surroundings. And by E equals mc squared, if the energy of the surroundings go up, the mass of the surroundings go up. I hope I'm making sense here. Looks like Build-A-Rat's got it down. Yep. Plus the energy, which has the missing mass equivalent, E equals mc squared. And so when the uranium atom loses mass and releases E equals mc squared, that E equals mc squared goes into the surroundings like the air molecules or whatever. They warm up, and because they've warmed up, they've gained energy and they gain mass. How much mass? E over c squared. M is E over c squared. So when you gain energy, you gain mass. When you lose energy, you lose mass. And as we know, when certain things gain mass, that mass, I should say energy, we're very comfortable saying that a system can lose energy to the surroundings, but we don't quite think of it a lot, that when the system loses energy to the surroundings and the surroundings gain energy, they also gain mass. Will passing gamma rays through a person make him Hulk? No, but I can make a Hulk solution for you. Let's pop the universal indicator back on here. Let's make a Hulk solution, shall we? We're going to neutralize the base that's on here. So I got about a couple more minutes. We're going to do this about 2 more minutes. We're going to try to make a Hulk solution here. And then I think I'm going to head on over to TikTok. So let's see here. Get a couple drops in. See if we can make our Hulk solution. A nice green solution. Thank you, MLM5. Thank you, Detonator. I'm adding hydrochloric acid, also known as stomach acid. Except the acid I'm adding is 100 times more concentrated than this, the acid in your stomach. We're going to get to green. Come on, baby. That might do it there. I probably went too far. Are we going to end at the Hulk? 3 more drops. Oh, there it is. There's your Hulk solution. Maybe another drop. It's just a little bit. No, I think that's nice. I think that hit it. It is a bit diluted. A little bit. We'll add a little more universal indicator to brighten up the color a little bit. Here we go. Get it in there. Yes, muriatic acid is HCl, and I have no idea why they have 2 different names. That's just the way it is in chemistry, man. We have 2 names for all sorts of stuff in chemistry. Yeah, if someone can maybe next time I'm out here tell me why muriatic acid is a different name for HCl, I'd greatly appreciate it. But hey, folks, appreciate you hanging out with me, and hope to see you next time we do a live. So long. Thanks for joining in.